and then we are live. I think we are live. I don't know. Let's check. I think yes. Fantastic. Finally I'm back. I missed you. You non-existent viewer. Well, here we are. Same thing, same old thing. Our RTS camera. We got the lighting going. That's fantastic. Now I would love to. Well, we have to finish our to-dos. So, find a way to use the same constant buffer definition for both HLSL and C++. Object constants. Well, okay, this one, I don't know about it. This is very temporary. RTS camera later. This is useful. This should be useful. How can we do it? Well, camera constants, light constants. Now let's go here and say constant buffer structures. Constant buffers. Constant buffer structures. Constant buffer structures. Our constant buffer structures, we simply or better struct so constant buffer structs, okay, constant buffer structs, constant buffer structs and constant buffers, because it's basically the same. Constant buffers, yeah, it's basically the same. So I can add constant buffer structs and then do a new HLSI constant buffer definitions. Okay, the constant buffer definitions include the constant buffer structs.hlsli, so camera constants, something like that, goodbye camera constants, light constants, goodbye the light constants header, object constants, oops, goodbye object constants header, so constant buffer definitions, fantastic, constant buffer light constants, here is camera constants, constant buffer camera constants, and here we put constant buffer camera constants, that's it, and then oops, no, don't care about it, and then oops, again constant buffer object constants, and here struct constant buffer object constants. Wonderful. Now we do this, we compile, include constant buffer definitions, oops, what, come on, compile invalid subscript camera constants, why? Camera constants, light constants, objects light object constant buffer camera constants, light constants, oh yeah, fantastic, everything should work. I'll do a rebuild. 3.5 seconds for a rebuild. Now this is cool, and you say why? You'll see my friend, you'll see. Now the mesh, don't care, the texture, CPU texture, to do, don't inherit from this we'll do it later once we generate the mip maps. Wrap. This is not true. When GPU texture, when, so here to do specify flag for generating mip maps. That's it. I'll do it when we talk about mip mapping. The math we don't care, but here in the properties, C++ general addition include directories, we got the project dir HLSL. Okay, apply your configurations. Look at this. When include here we need another folder, call it HLSL-I, where we put our we don't care. We can simply include the constant buffer structs.HLSL-I. I can do this. Oh yeah. I don't like it. I would love to have HLSL-I duck or Lucy, something like that. So the idea is that we do HLSL. Okay, we add a new folder, HLSL-I. We add to that the Lucy folder, and then we take all our, put it in there, am I breaking something? I may be breaking the HLSL thingy though. HLSL compiler, general, addition include directories. Project dir HLSL-I. Okay. All configurations. These now should work. HLSL-I. So these don't care. These don't care. These don't care. This is something like Lucy. Oops. Duck. This is something like Lucy. And this is like Lucy. If I compile, everything should work fine. Cannot open Lucy. Why not? Oh yeah, right, because in the properties for the C++ general, this should become HLSL-I. Fantastic. If I do this, everything will break. Missing type specifier, not a problem. Here the trick is to simply say, let's look at this. Define matrix as matrix. Okay. Define float3 as vector3, and here we say undef matrix undef float3. To do hack could be done better if we wrap simple math into custom matrix and float3 types. So we define the matrix with matrix, we define the float3 to vector3, we include, so we copy this, these will be substituted however we want, and then we undef the matrix. This basically means that, oh, let's use matrix kek. Oh well, matrix undeclare identifier. Okay, let's do this, rebuild. Now everything should work fine, but we're not using them. So constants here, constants, we have 3 constants, thingies, constant buffer, camera constants, constant buffer, object constants, constant buffer, light constants. Camera constants, constant buffer, camera constants. No. This is constant buffer, light constants. This is constant buffer. This is constant buffer, and voila! The effect is that we've used the same definition of our constant buffers in the HLSL code in our C++ code. Thank you includes. This is very cursed, not gonna lie, but I mean, we're talking. This is cursed, not gonna lie, but this allows us to have one single constant buffer definition, okay, which is very useful, because the other way with having to mirror the same definition both in HLSL and C++ was very error prone, because if I'm in a rush, I modify one, not the other. So basically use a single definition for both C++ and HLSL side constant. Use a single definition for both HLSL constant buffers. Voila, commit, push, done. Fantastic. Okay, so we have added other to-dos, but obviously these to-dos, I've added them because yes, I need to do them, but it's not very important. Don't inherit from DirectX scratch image, meaning do it yourself. Like just use a chunk of 8 bits, 8-bit integers. Okay, with some information attached. That's what I mean. So basically, don't inherit. Just have something like something like this, basically. std unique pointer unsigned short or I don't know, uint 8t, something like that. Okay, and pix and data. Okay, that's what I mean with that. So good to do. And maybe CPU texture format and format. Okay, something like that. And then go on. Don't do that. That's what I mean. The other to-dos that I have, so this is the obviously these two. Specify flag for generating maps. Yes. Do it after fixing CPU, after doing CPU texture to-dos. Wrap simple math and expose by from API. Maybe. May not. Oops. If present ever crashes, then fix it. Present did not crash up until now, so it's perfectly fine. This is an hack. Could be done better if we wrap simple math into custom matrix and flow-free types. Hard-coded, very temporary, but it's still useful. Factor out RTS camera code. Yeah, we could do it, but I don't want to do it explicitly because I don't want to impose any sort of structure and whatever. I can leave it there for now. This should go into something like camera update. That's the camera. Put game logic here. It's just a note for later. So okay, basically fix. So add some and comment some to do and better comment some to dos. So that's it. Oops. Now it's time to start thinking about so we got the lighting, we got the camera, we got the input, we got like the loading models, we got the input events, we got obviously textures, lighting, already told you, the UI, the bug UI, so we have a lot of groundwork covered. Is this enough? No, obviously. What shall we do next? Well, I was starting to think about the game per se. I was starting to think about the game. In particular, I was starting to well, I'll do it later maybe. It's a better idea not to stream signing in. So what I'm thinking, why the notes? Let's do the notes. It's fine. I was thinking, look, this is, so the game, what's the game? So yeah, Lucy is our framework. Okay, the game basically in some way uses the framework. Okay, and it's a real time tactics game inspired by Total War games. Only the battle part, so only battle part. Okay, now my idea of the game is that it will be basically a sequence of battles, so a sequence of levels. Okay, each level is basically, well, it's just a sequence of levels. Each level poses each level is centered around a battle, basically. Okay, a skirmish, whatever. So sequence of levels. Each level sees the player command a set of units to accomplish a given task. Okay, the enemy, so there will be enemy units whose aim is to stop the player from from accomplishing the task. Okay, so the idea here is that this is a sequence of levels. A level obviously will have like win conditions, lose conditions, the player units, the enemy units. I don't know if there will be ally I don't know how to write it. Ally, like that. Word reference. Okay, fantastic. Ally units. This is a don't know. So win conditions, lose condition, so basically player units, enemy units, and maybe ally units. There may be allies. Okay, so that's the three archetypes that we will have, okay, of units. This is a maybe. And obviously the this leads to a confrontation. So this situation right up here, so the player having a task that needs to be accomplished, and there will be an enemy that will try to stop the player from reaching the task. Well, this leads to some form of confrontation between the player units and the enemy units. Okay, so some sort of confrontation. Okay, that's the key. So the idea of the level is to basically win the confrontation. Has to use the player has to win. Deploying deploying one or more tactics. Okay, that's it. A level has its own win conditions, lose conditions, the player units, the enemy units, the ally units. That's it? Well, no. Has an environment. An environment in which the confrontation takes place. Okay, what's the environment? So win conditions, lose conditions, the player units, the enemy units, and the environment. Let's talk about the environment. Why? So obviously my idea is to focus first on the environment. Why? Because once I have the environment, then I can place units in the environment and make them interact with the environment. And once I have units, I can talk about players, so commanding the units, or having an AI that tries to be confrontational, so tries to stop the player, or have an AI that tries to help the player. So that's it, in which the confrontation takes place. Okay, the environment in which the confrontation takes place. Now, what's the environment? So basically, this is a sequence of levels. This is a level. The environment the environment will have some form of terrain. Okay, and I was thinking about a height map. Terrain approach. Okay, like in Total War. Then we will have buildings such as walls, bridges, like towers, and whatever. Okay, and then we'll have environmental elements such as rocks, trees, bushes, grass, etc. Okay, so the idea is that some will have I don't know, rocks, I don't know. I don't really know about rocks. But what I don't really know about bushes, I don't really know about grass, but what I want is trees. Okay, trees that have a gameplay, like component. Hiding troops, for example. Okay, we will also have rivers. Okay, hinder troops. Or stop, like it depends on how deep is the river, if it's shallow or not. Marshes, so rivers, marshes and whatever. Okay, this also hinders the troops, for example, or stops the troops or whatever. These I'm throwing. Here I'm throwing. For sure I know that I'll have walls, bridges, towers, trees, okay? So we have a terrain, this for sure I know. Buildings, this for sure I know. Environmental elements, of course we'll have some other environmental elements just for the trees, okay? It's a crucial gameplay element to hide the troops. Then we can talk about marshes if we want later, okay? So I wanted to start from the terrain, and in order to start from the terrain, I've never implemented terrain, and I had two ideas. One idea, the first idea was using like marching tiles, marching squares, with the height, basically. The second idea was simply using a height map. And I think this would result in something like this. Like you have your set of tiles, and then basically each tile will have a given height, for example, and then you do some interpolation, okay, to get a smoother sort of terrain that does what it needs to do, okay. I don't really like it because it's too blocky, okay. It's blocky. Blocky. It's also very limited. What I think is that I'll go with the height map, but the problem is that I've never implemented a height map terrain, so we need to learn how to do it, okay. Examples of I don't need marching cubes because I don't need the caves. Height map terrain. Something like that, not at this sort of resolution. I don't need this sort of terrain, but the idea is that to take an image, such an image, and turn it into basic. Each pixel gives the height of a vertex, and then you just put that into into a mesh, okay. So basically each pixel gives the height of a mesh grid, of the vertex in a mesh grid. That's it. Yeah, exactly, something like this. Basically each vertex here is displaced using the height map. That's basically it. So we need to study how to do that. So Dark 3D 11 height map terrain implementation. Procedural generation algorithms. This is also useful for okay. You see something like that basically. Obviously we are gonna do it on a smaller scale, like I'm not gonna have the height map of an entire country. Of course. I think the best two sources are here. Yeah, the OGL dev thingy and the Simon dev terrain generation. Here goes in like simple biome, we don't really care about that, but the other things and the techniques that are used, that are explained, could be used. So we need first to learn. I've already watched these first two videos, so that's it. Here I've already watched some of them. So the idea is that I'm gonna take notes on how they do it, and then I am going to like implement it myself, basically. So let's see.
Guys, today I'm very excited to announce a new series on this channel on the topic of terrain rendering. What I'm going to do is basically follow along this great book, Focus on 3D Terrain Programming by Trent Pollack. This book is part of the game development series, and notice that the editor of the series is Andre Lamotte. I actually did a review of a classic title by Andre with an implementation. Naturally, I'm going to replace all the fixed function APIs with an implementation using the modern OpenGL programmable pipeline. There doesn't seem to be many books on this very interesting topic. I actually own a similar book from the same time frame, so if this series turns out to be successful, I may very well extend it to cover new material from the other book. So what are we going to learn here? We're going to start from the very basics of height maps, what they are, how to load and render them. Then we're going to learn how to generate height maps ourselves using two different algorithms. And then we will use multi-texturing in order to throw a nice texture on our terrain. Next comes lighting, and again there will be two different algorithms to add lighting to the scene. The next step is much more advanced and challenging. Here we have GeoMip mapping, an algorithm that enables continuous level of detail. This basically means that the part of the terrain that is closer to the camera is rendered using more triangles than what is further away. We will also learn how to use frustum culling in order to avoid rendering patches of land that are outside a visible part of the scene. And for dessert, we have a few outdoor effects. These are not strictly speaking terrain algorithms, but they do help add realism to the scene. So here we've got a very basic water effect, as well as a skybox and a sky dome. And finally, we will generate random clouds and also stars. Oh, and let's not forget that someone is probably going to travel on that terrain, so we will implement some very basic terrain collision detection,
the music,
to keep our hero on the ground. So make sure to get your free tickets today by subscribing and hit that notification bell so you won't miss any episode. Thank you for watching, and I hope to see you in the first episode of Terrain. Welcome to the first episode of Terrain Rendering. In this series, we're going to implement most of the algorithms from the book Focus on 3D Terrain Programming by Trent Pollack using modern OpenGL. I've made many changes along the way, and I'll do my best to highlight these changes and explain the logic behind them. A terrain is obviously a very important feature in any game which takes place outdoors, and it will usually be the largest mesh in the scene. The terrain in this series is going to be represented using a grid of quads that stretches from left to right along the x-axis and into the distance along the positive z-axis. The different y values at each vertex make it look like an actual terrain. I'm using a left-handed coordinate system, but with minor tweaks you should be able to change this into a right-handed system. Each quad in this grid is divided into two triangles, and the entire structure will be maintained in its own vertex buffer. Since most of the vertices are shared
So, first thing to take note, here, this is like a game design and programming notes. This is like terrain. This, let's rename it to closer. Okay. Now, OGL dev uses a left-handed coordinate system we use a right-handed system.
between 6 triangles, we will also use an index buffer in order to avoid vertex duplication. Generating such a grid is pretty simple, but the question is, where do we get the y values for the vertex? Such a grid is pretty simple to avoid vertex duplication.
A single vertex is shared among 6 triangles. Okay.
Generating such a grid is pretty simple, but the question is, where do we get the y values for the vertices? One of the simplest solutions to this problem is to use a height map. A height map is a matrix or a table where every cell contains a height, which is the y value for the corresponding location in the grid. In this lesson, we will bring up the infrastructure for loading and rendering height maps. This infrastructure will be improved with many features throughout the series. Before we get started, I'd like to give you a quick overview of the framework that we will be using. If you are familiar with my OpenGL tutorials or you have your own framework that you are comfortable with, feel free to skip ahead using the time codes. The terrain code itself can be easily integrated into any framework. Basically, every episode in the series has its own directory with its own terraindemo.cpp file with the standard main function. The main function allocates a terrain demo application object, initializes it, and calls its run function. We will take a look at these GL calls in a minute. The terrain demo class is very simple. It has several functions to create a window using the GLFW library, configure the GLFW callback functions, and initialize a camera. There's also a function for initializing the terrain, which we're going to fill up with some code later. The run function waits until GLFW signals that the window has been closed. It calls the render scene function, which is where we're going to build up the frame. It also swaps the buffers and polls for events. Standard GLFW stuff. Right now, the render scene function only clears the back buffer. We also have 3 callback functions for handling the mouse and the keyboard. Note that you can quit the application by clicking on Q or Escape, and that the W button always toggles between wireframe and full polygon mode. The function createWindow uses a utility function called GLFW-init to take care of creating the GLFW context and the window. Again, standard GLFW stuff. Init callback registers the 3 callback functions that we saw, and init camera initializes the position, target vector, and perspective projection information for the camera. This is the same camera class that I've developed over the course of 3 of my OpenGL tutorials, so you should check them out if you are not familiar with that, but any camera code that you already have will probably work just as well. The class also contains private attributes for the GLFW window, the camera, and the wireframe indicator. We're going to add more attributes as we make progress. Back to the GL calls in the main function, we can see that we are setting the clear color to black and enable backface culling. The triangles will be specified in clockwise order. No special reason for that, but if you change this, make sure to fix the code which actually initializes the indices. And we also enable the depth test. If we run this
counterclockwise. Front counterclockwise, while here
the indices, setting the clear color to black and enable backface culling. The triangles will be specified in clockwise order.
Okay. OGL use clockwise winding order. For triangles, we use counterclockwise winding order for triangles.
No special reason for that, but if you change this, make sure to fix the code which actually initializes the indices. And we also enable the depth test. If we run this right now, we should be getting a nice empty window, and we can do the first step, which is to load the height map. For that, we're going to create a class called baseTerrain to store and render the height map. I'm going to write the important pieces of the code, except some boilerplate stuff like include files, declaring if and defs in the headers, things like that. You can find the link to the full source code in the video description. Right now this class has an empty constructor and we need a function to load the height map from a file. We're going to add a protected attribute for the height map itself, and for that I'm using a utility class called Array2D, which I've already created. This is a very simple wrapper for a buffer of memory, and it provides access to it as a 2-dimensional array. The class is templated on the data type of the buffer, so the same code can be reused for different data types. In the constructor we provide a number of columns and rows, and the number of bytes that we allocate is the number of rows times the columns times the size of the data type. The class provides several functions for accessing the data as either a 2D or 1D array. There are a lot of checks all over the code to make sure we are not making an invalid memory access. So our height map is a 2D array of floating points. The book actually uses an 8-bit height map, but I found out that floating points provides a much smoother terrain and overcomes various visual anomalies.
Okay, so they need use 2D array of floats.
In addition to the height map, we need an attribute to store the size of the terrain. For simplicity, the terrain will be square, so the width and depth of the height map are equal to the terrain size. Now let's write the function load from file. Again, I'm using a utility function that I already have called readBinaryFile. This function takes the name of the file and returns a pointer to a buffer with the contents of the file. We also supply an integer parameter as a reference, and readBinaryFile will populate it with the size of the file, which is also the size of the returned buffer. Notice that I'm not doing any checks on the returned pointer because readBinaryFile will exit on any error. readBinaryFile is very simple. It uses fopen to open the file as binary, stat to get the file size, and fread to read the file contents into the buffer that was allocated according to the size. The file is closed and the buffer is returned to the caller. Back to load from file, let's make sure the file contains a whole number of floating points. The terrain size is calculated as the square root of the file size. Don't forget to divide by the size of a float before calling square root, because that's the size of the basic element. We can now initialize the height map using the terrain size as both the rows and columns of the 2D array. This constructor takes a pre-allocated buffer. Notice that the array constructor takes a pre-allocated buffer. Notice that the array2D class always deallocates the buffer in the destructor, regardless of whether it was allocated internally or externally. In this case, the buffer was allocated by readBinaryFile, and it will be deallocated by array2D. Now I'd like to make sure that the file was read correctly, so let's add a temporary call to an array2D function called printFloat, which will print the contents of the height map. Let's go back to the terrain demo class, add a base terrain as a member, and in the initTerrain function we'll call load from file using a height map which is checked into the Git repo. Let's run this, and as you can see, the contents of the file looks okay, at least in the sense that there's no evidence of garbage. Okay, we are now getting to the core of this lesson, which is to use the height map in order to render a terrain. I've made a design decision to separate the management of the OpenGL stuff from the terrain. In the future, this will allow us to write a sort of a rendering backend in other APIs such as Vulkan and DirectX, while keeping a lot of the code unchanged. The OpenGL stuff will be maintained in a class with a very original name, TriangleList. This class will create and render a grid of triangles while taking their height from the height map. TriangleList needs attributes for the width and depth of the grid. While the terrain is square, I decided to make this class a bit more generic to make it easier for me to reuse it in my future projects. We also need handles for the vertex array buffer, the vertex buffer, and the index buffer. So create a class keeping a lot of the code unchanged. In future to separate the height map in order to render a terrain. I've made a design decision to separate the management of the OpenGL stuff from the terrain in a changed TriangleList. This class will create and render a grid of triangles while taking their height from the height map. TriangleList needs attributes for the width and depth of the grid. While the terrain is square, I decided to make this class a bit more generic to make it easier for me to reuse it in my future projects. We also need handles for the vertex array buffer, the vertex buffer, and the index buffer.
Okay.
If you're not familiar with these concepts, make sure to watch my OpenGL for Beginners series. The attributes are private, and we need a public function to create the TriangleList. This function takes the width and depth as parameters, as well as a pointer to the terrain in order to get the heights. We also need a function to do the rendering. In the create TriangleList function, we store the depth and width, create the OpenGL state, and populate the buffers. Before we exit this function, we disconnect our VAO, vertex and index buffers from the OpenGL state. In the createGL state function, we allocate and bind the VAO as well as the vertex buffer. I'd like to start by simply rendering the grid of vertices as points, so let's postpone the indices for now. Next, we need to define the layout of the vertex buffer. Right now our vertex only contains the position, but later we will also have a normal and texture coordinates, so let's define a structure called vertex with an attribute for the position. This structure has an initialization function that takes the terrain pointer as well as the x and z coordinates. We can now enable the vertex attribute and configure it for the 3 floating points of the position. The vertex attributes will be packed together in the same buffer, so we can use the size of the vertex structure as the distance between 2 consecutive positions. I'd like to make it easier to add attributes later on, so let's define a variable for the number of floating points in the layout. The last parameter of GL vertex at3 pointer is an offset in bytes, so we need to multiply the number of floating points by the size of a float. We will also increment it by 3 to make it ready for future attributes. Okay, let's hope that the OpenGL state is set up correctly. The next stage is to populate the vertex buffer with the position of the vertices in the grid. We prepare a vector of vertex structures. The width and depth of the terrain represent the number of vertices along the x and z axes, respectively, so we multiply them to get the total number of vertices. The function initVertices will perform the actual population of the vector with vertex positions. Once the vector is fully populated, we call GLBufferData with the size of the vector in bytes. This value is obtained by multiplying the size of the first element in the vector by the number of elements. We also pass in the address of the first element in the vector. Let's see how to initialize the number of vertices along the x and z axes, respectively. Vertices will perform the actual population of the vector we call GLBuffer. Initialize the vertex.
I was a bit confused.
This is actually very simple.
For the width and the depth, if it's a square, but if it's a rectangle.
Simple. We perform 2 nested loops over the depth and over the width. We call initVertex on the current element in the vector and move the current index to the next element. Let's write the initVertex function. For now, we will initialize the position using the x and z coordinates and set the y to 0. We will later use the terrain for the height. All we have left is to write a render function. This requires binding the VAO and calling GLDrawArrays using GLPoints as the topology. The first vertex is 0 and the total number of vertices is the width times the height. We have a few more things to do before we can render. First, we need a couple of shaders. In the vertex shader, we declare the layout of the position. We also have a uniform for the combination of the view and projection matrices. Usually in rendering there is also a world matrix, but our terrain is constructed directly using world coordinates. This means that I'm not going to scale road.
Okay, so square terrain mesh. Is in world space. Okay, but we could do it in like model space.
Or translate it. The main function just needs to extend the position to a 4D vector and multiply it by the view projection matrix.
Yes.
As usual, the result goes into the GL position variable.
Okay.
In the fragment shader, we declare an output variable for the color. For now, let's just set it to white.
Yes.
Okay, we need to compile and link our shaders, and for that I will use my existing infrastructure, which is based on my technique access to the series.
Okay.
Add the triangle list and terrain technique as members in the terrain. In addition, I'd like to factor out the file loading stuff from the load from file function because we need to do more stuff there. The init terrain function just needs to call init on the terrain technique member. This will compile and link the shaders. Load from file now calls load heightmap file and then create triangle list. The last change in this file is the render function. It takes the camera as a parameter and extracts the view projection matrix from it. As I said, if you have a working camera implementation, you should be able to use it to generate this matrix. Next, we enable the terrain technique. This simply calls GLUseProgram using the shader program handle. And finally, we call render on the triangle list member. The very last thing that we need to do is to call the terrain render function from render scene. Okay, if everything was done correctly, we should be getting a nice point grid. Now let's use the height map. The triangle list class will access the height map information by calling getHeight using the x and z coordinates.
Okay.
We just need to pass the parameters to the array2d get function. It will verify that the parameters are valid and fetch the value from the corresponding location in the 2D array. Now let's go to the init vertex function and get the y value by calling getHeight on the terrain object. We should now get a nice slope for our terrain. Alright, with a few changes we should be able to turn this point grid into a triangle grid. First of all, let's generate a handle for the index buffer and bind it to the GL element array buffer target. Theoretically, we don't really need vertex indices here. We can continue using GL draw arrays and render triangles, but we will need the indices when we get to normal vector generation, so it's better to get the infrastructure working right now. Let's prepare a vector for the indices. How many indices do we need? Think about the point grid as a grid of quads. The number of quads along the two axes is the number of vertices on each axis minus 1. Each quad has two triangles, so we calculate the number of quads and multiply it by 6 to get the total number of indices. The indices will be populated by the init indices function, and after that we do a second call to GL buffer data to upload the indices into the index buffer. Generating the indices is just a bit more complex than the vertices. We do the same nested loop, but this time we stop one vertex before the end because we are actually processing quads and not independent vertices. For each quad we calculate the index of the four corners. The basic formula is to multiply the current z by the width and add the x. The other three corners are calculated by adding an extra vertex to one of the axes or both. We can now generate the two triangles. First the so-called top left and then the bottom right. The last change is in the render function. We change GL draw arrays to GL draw elements and use GL triangles as the topology instead of GL points. The number of indices is exactly the same as before. Okay, let's run this, and as you can see it's a bit difficult to tell what's going on, so let's make the color dependent on the height because higher places are usually more exposed to light. We add an output color vector to the vertex shader and set all components to the y coordinate of the position. Now we need this to go from 0 to 1, and I just happen to know that the maximum value in this height map is 200, so let's divide y by 200 in order to normalize it. In fragment shader we add an input vector for the color and we copy it into the output variable frag color. Alright, much better. Now I'd like to point out a possible deficiency in the current design. You see, the triangles are very small and the only way to get a larger terrain is by using a larger height map. This is because the vertices, specifically the x and z, are generated using integer numbers. I'd like to introduce a concept called world scale, which allows us to scale the x and z up or down. We can easily do this in the vertex shader using a uniform variable, But since this scaling factor is known up front, it's better to simply combine it directly in the vertex buffer and just forget about it. So let's add a private variable to base terrain called world scale, which by default is 1. We provide it as a parameter to the init terrain function, and we also need a getter function for it. And now the init vertex function can fetch the world scale from the terrain and multiply it by the x and z. Let's try a world scale of 4, and it looks very nice. Okay, we've made good progress. In the next video we will learn the first out of 2 algorithms to procedurally generate the height map, so you can start creating terrains on your own. Thank you for watching, and I hope to see you in the next episode of Terrain Rendering.
Okay. 1820. Okay guys, I'll keep going on like tonight, so don't worry, I will keep studying like the terrain. Right now I already like, so he does the CPU side, height, displacement, okay. I don't think we need to load the height map from a file. For us, like the terrain is just like a grid of floats. From this grid we generate a terrain mesh, like we generate a mesh, okay, and then we render the mesh. As any other mesh, for now at least. We render the mesh. The mesh will be a the square grid of quads. So we'll have something like that. And x, y, z. So this is the x-axis, this is the z-axis, okay. This is the origin, so this is 0, 0. So this is 1, 0. This will be 1, 0. This will be 1, 1, and this will be 0, 1. So it will be generated in such a way, okay, and this, so for example, if the terrain side is 5, okay, I want 1/5. The terrain side is 4, 1/4, 2/4, and 3/4. So I have 1, 2, 3, and 4. Okay. So this is basically like 1/4. This is 1 2/4, and this is 1 3/4. So it's everything is normalized scale, rotate, translate. Okay, so grid of floats, a scale, grid of floats like a size. Or better, this could be a terrain subdivision. A subdivision factor. Then we want a position, a rotation, and a scale, as always. A grid of floats, and we are done, basically. For now, at least. Yeah. Something like that. We build it on the CPU, then we create the mesh and we render the mesh. It's a square grid of quads, something like that, and we do something like so 1, 2, 3, 4, so we do 1, 2, 3, 3, 4, 1, something like that. Okay, quad. Quad indices. Okay, so we can generate it like line by line, row by row, and then we can generate the indices however we want. So the indices for the first quad are that, the indices for the second quad are that. Counterclockwise. Okay, yeah. Okay guys, let's see you tonight. Bye bye.